Let's explore a little bit about what is known as continuity. Continuity, it relates a couple of things in mathematics together, I guess you might say. We've been talking about limits, so it's going to relate limits to something else that we talked about. As far as a simple definition of continuity, it's really pretty easy. We'll get into the formal definition more here in just a second, but a function is continuous. If you have the graph of a function, you can tell whether a function is continuous just by where you have to lift your pencil to draw it. Anywhere you don't have to lift your pencil, the function is considered to be continuous, and where you have to lift your pencil to go to the next part, so to speak, that's called that would be discontinuous there. So just a quick example here. So yeah, if I got this, and then the other part jumps down here. So this function's continuous as long as I don't have to lift my pencil, but here, let's call that 1. At x equals 1, I've got it where it's not continuous, or discontinuous, okay? So it's continuous everywhere except 1. For whatever function this is. Okay, so that's a pretty simple definition. If you have the graph, it's really easy to tell where your function is continuous and where it's not continuous or discontinuous. It's discontinuous, it would be said then at 1. But that's what we're going to explore here, is how do we define that mathematically? And the way we do it is actually with limits. All right, so here's the definition of continuity. It's looks fairly simple. A function is continuous. Function f, let's call it. A function f is continuous at a. A is just a general value of x, we're going to call it. So a function f is continuous at a if the limit as x approaches a of f of x equals f of a. You know, we've been saying, or we said, when we started limits, the function value doesn't really have to match the limit. The function value at whatever value x is going to, it doesn't have to match. But to be continuous, where you don't have to lift your pencil, so to speak, when you graph it, to be continuous, the two have to be equal. Okay? So this doesn't have to happen. I mean, we saw a lot of times when the limit doesn't equal the function value. But if it does, the function is said to be continuous at a. The way they break it down is there's really three things going there. Call it the continuity test, or it's tied in very closely with the definition there. There's three things that must happen for x to be continuous at a, f to be continuous at a. Number one, the limit as x approaches a of f of x must exist. So you've got to have a value for the limit. Well, same thing for the function value. F of a must be defined. And then the third thing is, number 3, I mean, you could have both of those exist and the other one defined, but you still have to have a third thing, and that is the two are equal. And so that, we can refer to that as the continuity test. If those three, if these three are all true, then F is continuous at A. Now what happens if one of them falls through? If one or more, if one of them falls through, then what do you think? Is it continuous? Could be continuous, right? If one or more of the three aren't true, so if either 1, 2, or 3, or 2 of them, or all 3 of them are false, if one or more of these 3 are false, then F is not continuous at A. Discontinuous, we would say. Okay? So it just gives us, this gives us a mathematical way of defining continuity. All right, so let's go with, let's go first of all here, let's look at a question or two from a graph. So I'm giving you the handout there, so I'm looking at the handout, continuity of a function handout. I'll just draw it up here. Roughly speaking. All right. Okay, so it comes up somewhere like that at 1, and it goes ways over like that at 4, and it goes down 5, and it jumps down to here at 5, and then goes up 7. Let's see, what am I missing? All right, so I need a P, yeah, I need a dot right there, okay. So this is up here. Looks like that's about 7. This is between, it's supposed to be between 6 and 5. This is at 1. So maybe, this is at 3. Maybe off a little bit, yeah, a little bit off. That one should have been a little higher. Something like that. Like I said, it's rough. A little better on the hand. Okay. So my first question on there, where is the function discontinuous? We'll call this function f. Where is the function discontinuous? Now, like I said, it's fairly easy doing it from the graph, figuring out where it's continuous. It's discontinuous wherever you have to pick up your pencil. And so this being an open circle there, that means there's a gap there. I mean, we designate with a circle. There's really not a circle there. It's just a gap, right? But to make sure we're clear about it, we put the circle. So there's a discontinuity at 1, isn't there? So where's f discontinuous at x equals 1? Let's just list them here because we are going to put reasons for it in just a second. Besides, we had to lift our pencil. That's not going to be a valid reason. But to find them, they're not that hard. All right, so then I have to go along, find until I get there. So again, I've got to jump there. So at 4, it's also discontinuous. And then at 5, and it ends at 7. So those are our 3 places where f is discontinuous. Now, let's explain our reasons based on the definition or the continuity test. We can dive into that if we want to, but because those, like I said, those two are very much related. All right, so let's explain using this definition of continuity. Well, let's go with x equals 1. Like I said, there's three things here that's got to be satisfied for this to be continuous. So if we're saying it's discontinuous, which one of these three doesn't meet the standard? All right, so we just, at x equals 1, let's look at it. Does the limit as x approaches 1 exist? Well, from the graph, for the limit to exist, we just look at left and right. Does the limit exist? Yeah, because from the left it's coming up to about 5.5, from the right it's coming into 5.5. The limit as x approaches 1 is 5.5. However, what about f of 1? Does f of 1 define? Yeah, there's not a point for f of 1. It's just open. So the reason it's discontinuous at x equals 1, f of 1 is not defined. There's not a point there. Okay? You with me there? There's no function value. All right, what about x equals 4? Same reason? It's not the same reason. The reason on that one is different. Oh yeah, this one's. We have a limit as x approaches 4 because from the left, from the right, we are coming into that 7 value. So the limit for 4, the limit as x approaches 4, is 7. We've got a limit, it's 7. We've got a function value. The function value at 4, what's the function value at 4? The function value at 4 is right here, it's 3. But what about the third part? They don't equal, do they? The limit as x approaches 4 of f of x, let's write that down, is 7. The function value at 4 is 3. So, the limit as x approaches 4 of f of x does not equal f of 4. That's really the reason. You've got a limit, you've got a function value, but they're not equal. Now what about number 5, or x equals 5? Do I have a limit as x approaches 5? Well, as again, doing the limit, you're looking at it from the left and from the right. Does that limit exist? It's coming up here. For this, from the left, our limit as x approaches 5 would be 3. From the right, the limit as x approaches 5 would be 1. So the left and the right there, I'm coming in here, and then I'm coming in down here. That limit doesn't exist. They've got to come in like up here. For the limit to exist, they've got to come in at the same level. The limit here doesn't exist. So number 5, the reason would be the limit as x approaches 5 of f of x does not exist. So they all three had different reasons. You see? So that's why you need all three. You got to have the limit exist, you got to have the function defined, and you have to have those three things equal. Okay? See how that works? Now, the other thing then they would ask is on number 2, on what domain intervals is the graph continuous? On what domain intervals is f continuous? What domain intervals is f continuous? Well, these are where it's discontinuous. So basically everywhere else, we have a function anyway. Everywhere else, it is continuous. So it's continuous. It looks like, yeah, you could say this just continues out here. It does stop over here, so we'll talk about that. But it does look like it goes on forever downwards. And so from negative infinity all the way, and we're talking about domain intervals, so x intervals. So from negative infinity, So out here, all the way until we get to 1 is continuous. We've got a solid graph. So that'd be our domain interval. Now it's discontinuous at 1, so I do the parentheses. And then from where else? So it goes all the way, it's continuous, I don't lift my pencil, from 1 to 4. So it's continuous from 1 to 4. And then it's continuous all the way until I get to 5, so 4 to 5. And then 5 to 7. Now I don't know what happens after 7, so I'm just going to cut it off at 7, 5 to 7. Okay? Those would be the places it is continuous. Everywhere it's not broken up. All right. Well, we're going to do the same thing, but we just, I mean, we could look at the graph, but this is essentially the same thing, but let's say, well, it does, yeah, it does different ways. Use a definition to explain why. Tell you what, let me do this first. Yeah. Where is the function discontinuous? So it's the same idea. And then explain it. So number 1, f of x equals 1 over x. Okay, where's that function discontinuous? Well, I mean, you can look at the graph. That's fine. But generally speaking on these, we're looking at denominator 0. Where is the denominator 0? So that would be x equals 0, wouldn't it? It's going to be discontinuous at x equals 0, because that would make the denominator 0. We're going to get a break at the graph. And like I said, you can think of the graph, look at the graph. Yeah, you got that vertical asymptote at 0. This is going to be discontinuous at 0. Now, explain, again, they want to use a definition. Why is it discontinuous at 0 based on that definition? Does the limit exist at x equals 0? What's the limit as x approaches 0? Doesn't have one, does it? The limit from the left is negative infinity, the limit from the right is positive. The limit doesn't exist, so there you go. Now, you can actually take your pick on this one because is the function defined at 0? The function is not even defined. So either one of those would be an appropriate disqualification there, I guess you might say. All right. Now let's use this one. We'll talk about this one. Use this one to talk about some other things too. All right, so we got f of x equals the greatest integer. I just talked about that previous section there. Yeah, so the greatest integer. That one you probably will need to look at the graph, won't you? What does the graph of that one look like? Well, it's those stair steps. Starts at 0, 0, but then you go to 1, jumps up at 1, 1 to 2, then jumps up to 2, 2 to 3, and backwards and forwards. Right? So, where is that one discontinuous? Well, at the breaks, at the jumps here, where is the jumps? It's the integers, isn't it? So this one's discontinuous at the integers. By the way, I don't know if you're familiar with, but the letter designation for integers is, it looks, usually you'll see it kind of as a fancy Z. So a way you could say this is X is an element. Kind of fancy. Must be a double. That's, wait, you don't have to write it that way. But you could say it that way. That's an element of symbol, and Z is the integer symbol. But anyway, that's why. Okay, now, how would he explain it, though? What's the explanation? Well, we've got function values at all the integers, because the function value at 1 is 1, the function value at 2 is 2, the function value is 3. But again, what doesn't exist? It's the limit, right? You don't have a limit as x approaches 1. The limit as x approaches 1, the limit from the left is this, the limit from the right is that. So, yeah, at all the integers, the explanation, yeah, the limit as x approaches a of f of x, where a is any integer, doesn't exist. Okay. All right, so yeah, like I said, you know, they could throw some different ones there, but, you know, if it's just a regular function, you know, fractional function, you're looking at denominator 0. So that's the sort of thing you're looking for there. But on the second one, on the greatest integers, that's a good place to talk about the continuity from the right and from the left. All right, so on number 2 there, the greatest integer, it's discontinuous at the integers. However, what we have is, on that, we have another special thing, and that is continuity from the right. So if a function is discontinuous at a particular value, it could be actually continuous, it said, from the right, if this f is continuous from the right. If the limit as x approaches at a, f is continuous from the right at a, if the limit as x approaches a from the right of f of x equals f of a. So like I said, this is a good example. The function is discontinuous at 1, but it's continuous from the right at 1 because, look at this, the function value at 1, so this is a good example. F of x equals the greatest integer of x is continuous, and I just picked 1, and you can do any integer. They work the same way. It's continuous from the right at a equals 1 since the limit as x approaches 1 from the right of my greatest integer is, so as I approach x is 1 from the right, that value is 1, isn't it? From the right, the limit is 1. And f of 1, the function value at 1, well, the function value at 1 is 1. So you see those two match up. And those two are equal, aren't they? So it's said to be continuous, even though it's discontinuous at 1, it's continuous from the right at 1. Because the function value equals the limit. Now guess what? if the limit as x approaches a from the left of f of x equals f of a, then f is continuous from the left at a. It's just vice versa. So if the limit as x approaches a from the left equals the function value, then you've got continuous from the left at a. All right, so just to give you an example here. Let's say we've got, that might be close to the one I did earlier, just a little different. All right, so our limit, so we got discontinuous at 2, right? Yeah. So that doesn't change anything about that. It's still discontinuous at 2. However, look at this. What's the limit as x approaches 2 from the left? What's the limit as x approaches 2 from the left? It's approaching 2 from the left, so I'm looking at that. So that is, I didn't mark it, let's say it's 3. 1, 2, 3. That's 3. What's the function value at 2? Function value 2, well, the dot's up there, isn't it? It's 3. So if those two things are equal, then the limit from the left is equal to the function value. That's continuous from the left, okay? So f is continuous from the left at a equals 2. Or x equals 2. Okay? So it's just the reverse here. If you look at the limit from the right at 2 is 1. Okay, so it's different than the left in the function values. All right?